Hello and welcome to Math with Mrs. Becker. Today in College Trig, we are going to look at the third part of section 4.1, where we are really focusing on radians and degree measurement. Today, we will be converting from one form to the other. So what that means is we will take time to convert from degrees into radians. And also, if you know the radian measure, we will convert it to degrees. In order to apply these conversions, we have to focus on the basic relationship that pi radians is equal to 180 degrees. Remember, 180 degrees is half of a circle. Pi radians is also half of a circle. So you can take that relationship and turn that information into a fraction. And notice that the fraction, you could have the radians on top, or you could have the degrees on top. To figure out which one you want on top is if you go ahead and look at the conversion. If I want to go from degrees to radians, the radians is the numerator. If I want to go from radians to degrees, degrees is the numerator. So whatever you want your final answer, whatever measurement your final answer should be in, that's what you want on the top of the fraction. Let's go ahead and try some. So if I am going from degrees to radians, that means I want radians on the top. So to convert 135 degrees, I would go ahead and multiply by pi radians over 180 degrees. Now what happens here is you cross cancel the degrees. It's no longer in terms of degrees. This is 135 pi over 180 radians. Now the last step is if you can divide the fraction, we have to. I can divide both 135 and 180 by 45. Another trick you can do, if this works, if your numerator is smaller than your denominator, your calculator will also help you to reduce fractions. You put the numerator in, so 135, fraction bar. Remember the fraction bar is right here. It's your A, B / C over 180. This tells you that your simplified fraction would be 3/4, which is what you would get if you divided both top and bottom by 45. So I would have 3 pi over 4 radians. And that is your final answer. So what that means is graphically, if I was graphing in standard form, if I graphed 135 degrees, the terminal side and the initial side would be in the exact same spot if I graphed 3 pi over 4 radians. Kind of cool. Let's look at another one. To go from degrees to radians, pi radians over 180 degrees. Degrees cross cancels degrees. So what I have is 540 pi, because remember it's top times top, bottom times bottom. So 540 times pi is how I got that. 1 times 180 is 180. I can cancel the 0 on top and bottom. Now if I look, 54 divided by 18, that's a whole number. 54 divided by 18 is 3. So I would have 3 pi radians. Done. One more where we're going from degrees to radians. Remember, you can have negative angles. It just means that the terminal side travels downwards first. To go from degrees to radians, you multiply by pi radians over 180 degrees. Degrees cross cancels degrees. Top times top. Negative 270 pi over 180. And this is in radians because the degrees canceled, so that's what we have left. I can cancel a 0. Both 27 and 18 are divisible by 9. So if I divide by 9, I would have negative 3 pi over 18 divided by 9 is 2 radians. There are lots of application problems where you will know the degree of the angle, but in order to use the formula that's provided, you need to be able to convert that angle into radians, okay? And we will see a lot of that on the back side of these notes. Let's go ahead and work the other way. If you are going from radians to degrees, then you want the degrees on top. So 180 degrees over pi radians. Radians cross cancels radians. Often, pi will cross cancel pi as well. Not 100% of the time, but very often that will be the case. You will have pi on the top, pi on the bottom. Now when I look, top times top, negative times 180 is negative 180. On the bottom, I only have a 2. Negative 180 degrees divided by 2 is negative 90 degrees. Let's look at the next one. To go from radians to degrees, 180 degrees over pi radians. Radians cross cancels radians, so now it's in degrees. Pi cancels pi. I'm going to go ahead, top times top. If I take 9 times 180, I have 1,620 degrees from taking 9 times 180. On the bottom, I have a 2. So if I go ahead and take 1620 and I divide it by 2, I have 810 degrees. Last one. I have 2 radians. So notice this is what I mean. You don't always have pi. A lot of time you do, but it's not a requirement for something to be in radians. It does not have to contain pi. So if I am going to degrees, 180 degrees over pi radians. Radians cross cancels radians. Top times top would be 360 degrees over pi. If you left it like this is radians. Oh, sorry, it's not radians. Radians canceled, my bad. So this is 360 degrees over pi. If you left it like that, you're fine. Or if that drives you nuts, like I would go crazy not knowing what that actually was. If I take 360 divided by pi, it would be 114.59 degrees. Okay, so there's some examples of how to do conversions. Again, we looked at both degrees to radians as well as radians to degrees. Now, here is one of the first formulas that they are going to have us work with. If I have a circle, okay, this is a central angle. A central angle means that the vertex of the angle lies at the center of the circle. This is a radius measure. This is a radius measure. When they talk about that, they're going to use the variable r. This is called the arc length. It's the measurement from one segment to the other, okay? This they call S. That's your arc length. The central angle measurement has to be in radians, and they call it theta. Now, this is a relationship that we will work with quite a bit. So if I want to find theta, you take S over R. So theta is the measurement of the central angle. There's your visual. S is the arc length. Okay, from one side of the angle to the other, how much of the circle is included. R is the length of the radius from the center to the side of the circle. Again, theta has to be in radians. So right now we're going to go ahead and find that central angle. So we have a circle. So I'm just going to go ahead and draw a central angle. Okay, we have a radius of 75 centimeters and an arc length is 55 centimeters. We want to find the central angle. So the central angle, that's what we're trying to find. Radius is 75 centimeters. Arc length is 55 centimeters. They told us the formula. I take S, so 55, over R, 75. I can divide both top and bottom by 5, and I can simplify this. If I have 55 over 75, it would reduce to 11 over 15. This is in radians. Again, if you went ahead and calculated that as a decimal, 11 divided by 15, you could also have 0.73 repeating radians. Okay, so we have the fraction representation as well as the decimal. Again, I just used this formula. Let's look at another one. Given a circle where the arc length is right here, that's S. This is 13 inches. The radius right here is 7.5 inches. Find theta. So theta is what we're trying to find. S, the arc length, is 13 inches. R, the radius, is 7.5 inches. So using the formula, theta equals S, 13, over 7.5. Now we cannot leave it like this. You're not allowed to have a decimal within a fraction. So what I did is I just said, okay, well, let's take this times 2. because what I'm doing here is canceling the decimal. 13 times 2 is 26. 7.5 times 2 is 15. So I said, all right, 26 over 15 radians. Again, if you are more comfortable working with decimals, if you take 13 divided by 7.5, you would have 1.73 repeating. Again, you're finding the central angle, which is in radians. Okay, let's look at the last one like this. Find theta. Theta is the measurement of the central angle. It's in radians. Here, so I'm trying to find theta. That's the question. Radius. The radius, if you look at the visual, is 3 inches. S, the arc length. This measurement right here is 6 inches. So theta equals S. S is 6 inches over the radius, which is 3. 6 divided by 3 is 2, and the label for theta is radians. Okay, so there's one way that we can use this relationship looking at the radius of a circle, the central angle, as well as the arc. Now on the next part, if we want to find the arc length, let's just go ahead, and what we just had was theta equals the arc length over the radius. We can rearrange this. If you want to find the arc length, which is S, you would just go ahead and multiply both sides by R. So S is the radius times the central angle. Again, the main thing here is you have to make sure that theta is in radians. So here's where you're going to see that we will have to do quite a few conversions. For a circle with a radius R, central angle theta, if it intercepts an arc with the length of S, the formula is S equals R times theta. Okay, so again, it's just manipulated from the original equation that we worked with in the previous example. So let's go ahead and find S. A circle has a radius of 4 inches. So R is 4 inches. Find the length of the arc. So we're trying to find S. S is we don't know. Theta, the angle is 240 degrees. Here's the problem. These equations only work if this is in terms of radians. They gave me degrees. So I need to turn it into radians by multiplying by pi radians over 180. Degrees cancels, so I have 240 pi over 180 radians. I can cancel the zeros. 24 and 18 are both divisible by 6. So I would have 4 pi over 3 radians. So that's what theta is. If I want to find S, here's the formula. R, which is 4, times theta. 4 times pi over 3. Top times top, bottom times bottom. This is 16 pi over 3. Now this is the arc length. So the measurement is going to match that of the radius. The radius was measured in inches, so the arc length is also going to be in inches. So another way that we can use that formula from the front side of the notes, we just had to solve it for S. The trick is you have to always make sure that theta is in terms of radians. So let's go look at another one. We want to determine the arc length. So if I have 138 degree angle is what they're telling me. So it looks something like this. The radius is 20 inches. So I know the radius is 20 inches. I want to find the arc length, so I'm not sure what that is. Theta is 138 degrees. Here's the deal. You cannot use that formula. We can't use arc length equals radius times theta unless theta is in terms of radians. So I need to go ahead and multiply by pi radians over 180 degrees. Degrees cancels degrees. 138 pi radians over 180. Again, I can show you that little trick since the top is smaller than the bottom to see if I can reduce it. 138 over 180. It should be 23 over 30. So 23 pi over 30 radians. That's what theta is. So now when I go ahead and do this, S, here's my formula. Take the radius times theta. So S equals 20 times 23 pi times 30. I can cross cancel these. I could divide by 10 top times top, bottom times bottom, this would be 46 pi over 3. Your arc length measurement is going to match that of whatever the radius was. So it's going to be 46 pi over 3 inches. One more, and then we'll talk about the area of a sector. Here is my measurement. So theta is 90. The nice thing is, once you really get used to those common measurements, like you'll just look at 90 and say, hey, 90, that is the same as pi over 2. Like if you see 180 degrees, hopefully you already say, oh, 180 degrees, that's pi. Okay, so there are some common ones that we will use quite a bit. So theta, if it's 90 in radians, that is pi over 2. Your radius, the measurement here, I can see it's 3. They don't have it labeled, so we say that it's units. S, this is the arc length. This is what they want me to find. Find the arc length. So S equals your radius times theta in terms of radians. So it's 3 pi over 2 units. Okay, let's move on. Our final idea for the day. What the heck is a sector? Well, the sector is a portion of a circle. Okay, it is the region that's bounded by 2 radii and the intercepted arc. So think of like a piece of pizza or think of a piece of pie. Okay, that's what a sector is. In order to find the area of a sector, as long as you have a central angle, meaning that the vertex of the angle is at the center of the circle, here is the formula. A is the area, 1/2 is a constant, r is the radius, so you have to take the radius squared. Theta, again, in this formula, it has to be in radians, okay? So I can use this formula as long as I know the radius of the circle and I know the angle of the central angle in terms of radians. Let's go ahead and look at our last example for the day. A sprinkler on a golf course fairway is set to spray water over a distance of 70 feet, and it rotates through an angle of 120 degrees. Okay, so for me, again, I need to draw this out just so I kind of have a visual. So it's going to sprinkle 70 feet, and it's going to cover an area, so it's like, okay? Can you like totally hear it? I can hear it. All right, so that's what it's doing. We want to find the area. So area equals 1/2 times the radius. Our radius is 70 feet. So it's 70 feet squared times theta. Now here's the problem. Theta is 120 degrees. This formula is set for radians. So I need to take 120 degrees to convert it to radians. It's pi radians over 180 degrees. The degree cross cancels. Top times top, bottom times bottom. 120 pi radians over 180. I can cross cancel a 0. That's the same as just dividing by 10. 12 and 18 are both divisible by 6. So theta is going to be 2 pi over 3 radians. So 2 pi over 3. So I just filled in the area. Area equals 1/2. Our radius was 70, so I squared that, turned 120 degrees into radians. We found that to be 2 pi over 3. Now when I multiply this, if I go ahead and look at this, oh, I see right away I can cross cancel. So if I have 1/2, 70 squared, I'm just going to rewrite it, 2 pi over 3. This 2 is on the bottom. This 2 is on the top. So just to kind of save myself a headache, I went ahead and cross-canceled that. It's going to help me so I don't have to simplify so much later on. 70 squared is 4,900. That's the same as 4,900 over 1. So when I multiply it, top times top times top, I have 4,900 pi over bottom. That cross-canceled, that's a 1, that's a 3. So again, 4,900 pi over 3. This is area. So this would be feet. Area is squared. 4,900 pi over 3 feet squared. Okay, those are some other topics from section 4.1. We will continue 4.1 tomorrow by looking at something called linear and angular speed. I hope you had a great time today, and I'll talk to you soon.